Hello everyone. My name is Alireza Asadian. I'm the technical director of MST Rebar. It's my great pleasure to be here today, and I would like to first of all thank Professor Amir Pham for inviting me to this webinar. The title of my webinar is the resilience and longevity of GFRP reinforcing bar in sustainable construction solutions. So in this presentation, I will give you a brief introduction about GFRP bars and the benefits of using GFRP bars. I will then talk about the available standards for material specification of GFRP bar, as well as the available standard for the design of GFRP reinforced concrete. I will show you some case studies on the longevity and durability and sustainability of GFRP reinforced concrete. Then I will talk a little bit about the carbon emission associated with the use of GFRP reinforcing bars in concrete structures. And finally, I will present some field applications where FRP rebars as internal reinforcement and MSD bar in particular was used. So as you may have seen in your everyday commute, our structures, our infrastructures, building, bridges are suffering from corrosion resistant reinforcement. And corrosion resistant reinforcement happens by penetration of chloride into concrete. Corrosion forms the volume expansion of the rebar and can induce more cracking, cover spalling, and exposure of internal reinforcement to aggressive environmental conditions. Also, it's important to know that corrosion is accelerated by carbonation of concrete that lowers the pH environment of the rebar. Corrosion can also result in degradation of the strength of the structure over time, and which can result in catastrophic failure. For example, this is a picture of a parking garage that collapsed back in 2008 in Quebec, Canada. And this incident unfortunately resulted in one casualty. And so the main reason for the collapse of this parking garage was the lack of regular maintenance to prevent the corrosive effect from de-icing salts. Another more recent incident that happened in Germany, the partial collapse of a bridge in Germany may have been caused by chloride contamination in the past. Obviously, engineers are aware of the issue of corrosion. They take additional measures to mitigate the issue of corrosion in reinforced concrete structures. I don't know if you see the cameras on the right side. It's a bit distracting for me. Engineers take additional measures to mitigate the issue of corrosion in reinforced concrete structures. Those measures are, for example, use of corrosion inhibitor admixtures in concrete, or use of alternative reinforcing bars such as epoxy-coated, galvanized, or stainless steel rebar, use of sealers and membranes on concrete surface, or providing additional concrete cover, and so on and so forth. It's, however, very important to know that those measures are, first of all, costly. They will add to the initial cost of the project. And more importantly, research have shown that many of those measures can only delay the issue of corrosion in best case scenarios and will not eliminate the corrosion issue in reinforced concrete structures. And that is why we think the use of MSD bar or fiberglass rebars will, first of all, address the issue of corrosion in reinforced concrete structures, and will add many other benefits that I will talk about in this presentation to reinforced concrete structures. Now, what is a GFRP bar made of? Or glass fiber reinforced polymer bars are a composite material that are made of fibers and resins. There are excuse me, there are many types of fibers and resins available in the market, but what is of interest from economical and durability point of view is glass fiber. We use the latest generation of glass fiber called ECR glass fiber. And the resin that showed a very good durability for construction application is vinyl ester resin. And in a cross section of MST bar or any high modulus GFRP bar, there is around 80 to 85% ECR glass fiber, and the remainder of 15 to 20% is vinyl ester resin. Now, what are the mechanical properties of GFRP bars versus conventional black steel rebar? GFRP bars have very high tensile strengths, but they have lower modulus of elasticity. The material is elastic up to failure, as you can see in the graph on the right side of this slide. However, the elements or reinforced concrete elements made with GFRP bars will have very good deformability, and deformability is essentially ability of a member to take very considerable deformation or deflections before failure. MST bar and other GFRP bars are very lightweight. They weigh only quarter of black steel rebar. Some GFRP bars, including MST bar, has a very good or very high bond strength to concrete. GFRP bars are non-conductive, both thermally and electrically. That can be of benefit in certain applications. And obviously, as I mentioned earlier, MST bar, GFRP bars are corrosion resistant. So following a slide, I will talk briefly about available codes and standards in North America for material specification as well as the design of GFRP reinforced concrete elements. It's very important to know that not all the GFRP rebars that are available in marketplace can be used in construction applications in North America. GFRP bars must meet the requirements of ASTM D7957 in the US, and in Canada we have a similar standard. It's more stringent than ASTM D7957 called CSAS 807. Some ministries of transportation in Canada and some departments of transportation in the US, they have their own material specification requirements that the manufacturer needs to comply with in order for their product to be eligible to be used in their projects. Now, what are the requirements of all those standards? Based on those standards, physical, mechanical, and durability properties of GFRP rebars needs to be checked through third-party testing and shown that they are all within the acceptable limits of those standards. Here is the list of some of those tests that the manufacturer needs to perform. Many of those tests we do on daily basis in our manufacturing facility in order to ensure that our rebar continues to meet the requirements of those standards. And I should mention here that in manufacturing more than 1,000 lots of rebar, we never had a failed batch of MST bar. Here are a few pictures of some of the tests that we have done so far on MST bar. When it comes to design of GFRP reinforced concrete, the most recent code is ACI code 440.11-22. This code was released in September 2022, and it's essentially building code requirements for a structural concrete reinforced with the GFRP bars. ACI 440 is what's called a sister code to ACI 318. That means that the chapter numbering, section numbering, and code language is very similar to ACI 318.19. For highway bridge design, AASHTO has AASHTO LRFT bridge design guide specification for GFRP reinforced concrete. In Canada, for building design, there is a standard called CSAS 807. That's for design and construction of building structures with FRP. Chapter 16 of CHPDC, or Canadian Highway Bridge Design Code, has some recommendation and clauses for the design of highway bridges with FRP. So following a slide, I would like to show you some case studies on durability, longevity, and sustainability of using GFRP bars in construction applications. So one of the durability test that is done based on CSAS 807 is resistant to alkali, and this test is done two ways: one with load and without load. So in with load test, the rebar is exposed to alkali solution with a pH of around 13, very high pH values, and then it's under a constant stress of 3,000 microstrain, and the rebar is then conditioned in an environmental chamber at the temperature of 60 degrees Celsius or 140 degrees Fahrenheit for a period of 3 months, and then after that, the conditioned or aged rebar is tested to check the tensile strength as well as modulus of elasticity retention of the rebar. So what you see here is the table showing the alkali resistant of number 5 MST bar under load. And this test we have done at the University of Sherbrooke in the Professor Brahim Bemukrin's lab. And as you can see, the average strain retention of MST bar was around 91% of ultimate tensile strength of MST bar, and the average modulus retention was 100%, meaning there was no reduction in modulus of elasticity due to exposure to alkali solution. And for your reference, the limit in CSAS 807 standard material specification standard is 75%. Another concern with GFRP bars is creep rupture, or the effect of creep over long term on the rebar. Again, we have done many tests at University of Sherbrooke with Professor Brahim Ben Mukrain. So in this test, the rebar is under different levels of sustained stress, and then the time to rupture of rebar under each stress level is measured or recorded, and then the experimental data is extrapolated to see the creep rupture limit for MST bar or any other GFRP bars. And as you can see in this graph, the creep rupture strains at 1 million hours, or 114 years for MST bar, was around 62% of ultimate limit state. And for your reference again, the limit in CSAS 807 is 35%, and the limit of ACI 440.11 code that is used for design of GFRP reinforced concrete is 30%. Another long-term effect on GFRP reinforced concrete elements is effect of fatigue under repeated loading. That is important, for example, for bridges or any other elements that are subjected to fatigue loading. Again, we have done some fatigue tests at the University of Concordia under the supervision of Professor Khaled Galal. So this I have a video showing a last few cycles of one of the tests. And so in this beam, maximum stress in MST bar was around 400 MPa, meaning around 60 KSI, and the beam was under fatigue loading at a frequency of 2 Hertz, meaning 2 cycles of loading and unloading on this beam. So this beam survived 2 million cycles of loading and unloading, and then the test was stopped since no failure was observed. And here is the last few cycles of that beam test. So the effect of UV exposure is another concern with for the long-term exposure of UV for GFRP reinforced concrete. Again, we have done some load testing, some UV exposure testing with Professor Brahim Ben Mukrain. So in this test, samples of MST bar was subjected to UV light for 1,500 hours as well as 3,000 hours, and then the scanning electron microscopy or SEM analysis as well as FTIR and internominal shear strains of the samples were measured. So as you can see in these pictures, some discolorations was observed as a result of exposure to UV lights. However, there were no degradation in terms of mechanical properties on the rebar, and this report concluded that there was no effect on the horizontal shear strength of MST bar due to UV exposure. The FTIR analysis confirmed that GFRP bars had not been chemically degraded by UV conditioning. Also, the SEM analysis of conditioned and unconditioned GFRP bars exposed to UV showed that no effect in polymer matrix or fiber or the interface were observed. So apart from all those laboratory testing, there has been several real-world case studies showing the good performance of GFRP rebars under real load conditions. The first case study I would like to present is a Ministry of Transportation of Ontario bridge. So this bridge is called Third Concession West Underpass over Highway 401 in Ontario. This bridge was originally constructed in 1968. Around 33 years later, MTO or Ministry of Transportation of Ontario have done a condition survey confirming that the deck replacement was appropriate. So the reconstruction of the bridge was completed in December 2008. Here is a picture of that bridge. MTO also done cost analysis for the bridge, and they have seen that the initial cost of bridge deck, without considering any saving over the life cycle of the bridge, was very similar to the same or similar scale bridges that were built around the same time. So showing that the GFRP bars, even back in 2008, were not that expensive compared to steel rebar. 10 years later, MTU have done a load testing on the same bridge, and they have concluded that there is no change in girder performance within this period. There is no change in GFRP bar performance, both longitudinal and transfers in this period. Also, they've concluded that there was no loss of elastic stiffness in positive and negative moment regions based on an applied live load. And finally, the last conclusion was that the GFRP reinforced deck performing very well in the first 10 years in service. Another case study led by Professor Antonio Nani is on a bridge in Texas. So similar to previous study, they have done some core sampling in this study and done some microscopic analysis as well as some shear tests on the samples. And again, they have concluded, similar to the previous project, that the microscopic examination did not show any GFRP degradation. Fiber did not lose any cross-sectional area, and the matrix appeared intact with no visible damage to the fiber matrix interface. The fiber also the fiber content was similar to the pristine bar performed in 2000, confirming that there was no apparent loss of fiber content for the rebars in this application. Another study done by Professor John Myers and Professor Antonio Nani is on the GFRP reinforcement in box culvert after 16 years of service. You see here a picture of old culvert and a new culvert, and again, similar to other case studies, they have taken some real core samples from the culverts to do the life or durability studies. They have done SEM image analysis, and similar to the previous project, they have concluded that the microscopic examination did not show any GFRP degradation, as well as fibers did not lose any cross-sectional area. The matrix was intact. No damage was observed at the fiber matrix interface. Also, the concrete GFRP interface was maintained properly and no interfacial bond loss was observed. And also, interestingly, they observed that the TG of extracted GFRP samples was 30% higher than that of control sample produced in 2015 by the same manufacturer. Also, similar to previous study, the result of fiber content, there was no apparent loss of fiber content in GFRP bars. And finally, they've concluded that this study confirms that GFRP bars maintain their microstructural integrity after 16 years of service in GFRP box culvert bridge. So in the following slide, I would like to talk about the benefits of using MST bar and GFRP bars from an environmental impact perspective, and show you how using GFRP bars can help the construction industry to move towards using cleaner or more environmentally friendly solutions. So as I mentioned earlier, GFRP bars are very lightweight. They weigh only quarter of a black steel rebar. So there will be a quarter CO2 emission from transportation of the rebar to the job site. GFRP bars will have longer life, so less demolishing of existing structures, less energy to use to recycle those structures, less concrete to use to build new ones, and all in all, less CO2 emission. GFRP reinforced concrete elements will be better thermal isolators because GFRP bars are not conductive thermally, and therefore less energy loss in buildings made with reinforced with GFRP bars. Also, very important to know that lower energy is required to produce MST bar than a steel rebar, and we'll talk about this point in my next slide. One interesting point to mention here is that fluoride is not a durability concern for GFRP reinforced concrete. This will bring a lot of opportunities to construction industry now. For example, sea sand and seawater may be used to make concrete, or there may not be a need to use fresh water to make concrete or to cure concrete. So this is I did a very small case study for a slab on grade with an area of 200,000 square feet to show you the difference in carbon emission from using MST bar compared to black steel rebar. So This study shows that the MST bar is 400% greener compared to the GWP or global warming potential of average steel rebar that are available in the marketplace. And if you compare the GWP of MST bar to the cleanest steel rebars that are available in the market, we are almost on par with those rebars. And those steel rebars are produced with 100% recycled steel rebar. So following the slide, I will show you some field applications where MST bar and on other FRP bars have been used, and most recent MST bars projects as well. So one of the the use of FRP bars have started in construction back in 1990s, but in the very first bridges, the GFRP bars were only used as secondary reinforcement, meaning, for example, top mat of a bridge deck. So over time, the owners, the engineers gained confidence on the use of the on GFRP rebars. Fast forward 25 years later, this is a bridge in Highway 11 in Toronto. And this bridge was entirely reinforced with MST bar. Another bridge deck example in Nova Scotia with MST bar. Another example in Toronto, a bridge deck. This is a picture of CIP bridge deck in Ohio that was reinforced with MST bar. I will show now a video on one of our project in Ontario. So in this video, you can see different shapes of MST bar that we can make, and also how easy handling of MST bar on the job site is. And you will also see that the tying of the rebar and all those practical applications are very similar to conventional black steel rebar. Take a look at the video. So another application is in caissons for soft eyes and tunneling application. You see a few pictures of some of our projects. This is Nickel Station in Ontario. Those caissons in the soft eye part was all with MST bar. Deep foundations. This is one of our most recent projects. The deep foundation in Toronto. Precast concrete culverts in Ontario, again with MST bar. These are pictures. This is a picture of a Churchill LRT station in Edmonton, Canada. All those slab-on grades are with MST bar. Another very interesting project. Those are sea hives in Florida. All those sea hives that you see in these pictures are 3D printed, and we had to meet very tight tolerances when we were producing our bent bar, and we have delivered obviously this project successfully without any issues. Coastal constructions are another applications where MST bar has been extensively used over the past. Those are pictures of Port Killington in Ohio. 1.2 miles of port was reinforced with MST bar. Seawalls in Florida, again, another great application for GFRP bars and for MST bar as well. You can see a few pictures of some of our projects with seawalls in Florida. ICF houses, low to mid-rise ICF houses now in Canada and in the US are reinforced with MST bar. This is a picture of one industrial building. It's with composite floor decking system. This structure was built in Washington, again with MST bar, all the slab-on grade as well as the composite floor decking system. All the deck slabs were also reinforced with MST bar. Industrial buildings, another example with MST bar. Agricultural structures, those are pictures of a slurry storage tank in Saskatchewan, Canada. Those tanks are to store animal waste, very corrosive environment for internal reinforcement. And this structure has been reinforced with MST bar. Now it's in service for almost 8 years without any durability issues. MST bar also being used for repair and rehabilitation of existing structures. Those are pictures of Panama's main corridor bridge that was repaired with MST bar. Another most recent repair project, this is a Louisiana Department of Transportation project. Again, the MST bar was used for the repair of this project. So one of the very big challenges for the engineers and for our industry was the lack of a reliable software to use and to design GFRP reinforced concrete with. And we have collaborated with Alter, and Alter team now implemented ACI 440.11 in their product lines that includes S concrete, S line that is for design of continuous beams and slabs with steel, and now with GFRP rebars, as well as S foundation. And this is to me, in my opinion, is a very big step for our industry to have a very reliable software for design with GFRP reinforced concrete. And this brings me to the end of my presentation. I would be happy to take any questions now.